What are you starting your trial on time?
I don't know.
We should like to start a few minutes early. To learn about transitions.
So we get the program. These are the programs. Yeah.
How's that sound? I don't hear any.
There you go.
Oh, it start. Okay. That's actually a little weird. I can't really hear the. I don't hear myself. I hear a little bit, but not much. Yeah, it makes sense. That is good. All right, I guess I don't need to necessarily project quite as loudly as I usually do. Is there more chalk? There is more chalk. Do-do-do-do-do. Yeah. I recognize the majority of people in this room right now, so I'll wait a couple minutes to see if anyone else is showing up. Currently, the non-graduate students outnumber the graduate students, so we'll also see if we can shift that balance.
So all lectures will be video.
Yes, that's fine. I'm there.
I don't know.
Back of the room, center of the room. You don't really have much else of a choice if you want to get a good shot of the area here.
Oh, I guess the ball is quite small.
I'm guessing it's zoomed in to such a degree that it fits about that thing. It's possible that some... Yeah.
The board on like one window.
It's a good thing I write relatively large. It probably also depends on the quality of the video. If they're streaming it sufficiently high quality, it should be fine. There's a chance that someone is actually like panning it side to side, but I don't know if anyone does that.
I'm just thinking with regards to like, even if I have it in high quality, my screen is sufficiently small.
Yeah.
Still not be able to read it because the text is too small on the screen.
Yeah, hard to say. I can write larger than that if need be. I have 6 full boards. I can write pretty large on that. At PIMS, I know when we did a couple online streamed lectures when Kai was in London, we just had a small little controller and you would just pan the camera over as appropriate. But that was a much smaller room than this, so you couldn't have a camera that far back. Yeah. It's kind of hard to do that a little bit because, if everyone just writes in nice linear order, moving along from one board to the next, it's probably fine. But if anyone's jumping back and forth from one board to another, it's a bit awkward. That helps a lot. I'll just give non-linear talks. Just start writing there, write a couple words over here, write on the back of the chalkboards, however one would do that. We have reached parity, if you include the speaker. Oh, parity is broken. Dang. If you don't include me, then we're at parity.
Oh, it's already 5 after.
All right, I should.
So we'll start here, first day of the graduate course of modular forms around string theory. So first day is by Simon Rose. Is the introduction to modular forms and some enumerative symmetry.
Well, so thank you everyone for coming. So I guess the format of these lectures is that this is intended to be a fairly low-level introduction. So if you already know something about modular forms, I largely apologize because you're probably going to know most of what I say. The end of the talk is going to be geared towards talking about quasi-modular forms, which is the more relevant thing, and I'm going to state a couple theorems that actually say how these come up enumeratively. And then apparently there's also some time this afternoon we're supposed to have discussion sessions. So not right now, but I do have a list of some computations, some lemmas that I could have said in this talk that I'm instead leaving to you guys to do later because, you know, it builds character. Okay. So in this talk, we will introduce a certain class of functions called modular forms, and we'll give some examples and some properties. And so these are generally regarded as pretty nice functions. In some suitable sense of the word nice. Now, for my purposes, I know there's a huge, rich arithmetic theory of modular forms. There are number theorists absolutely love this stuff. There's these Hecke operators and all this fun stuff you can do. Fermat's last theorem, something, something, something. They're generally a very beautiful field of study. However, I admit that for my purposes, I admit that I'm a little bit narrow-minded about these. I think of them simply as generating functions with nice coefficients. So your mileage may vary. That's how I think of them, and honestly, most of this talk is largely going to be geared towards that, although of course I'm going to give the right definition. But honestly, even thinking of them as generating functions with nice coefficients, they're still really cool. So to actually define modular forms, so again, this is going to be the elementary part. So first of all, we need to talk about the modular group. So PSL2Z is, well, you can think of it a number of different ways. It's a subgroup of PSL2R, PSL2C, but we can think of it as the group of 2x2 matrices up to, well, equality, you know, up to multiplication by -1. So the reason we care about this particular group is that it actually acts naturally on the upper half plane. The upper half plane, which is given by, of course, a plus bi, complex numbers, such that b is greater than 0. And of course, this action is given by a, b, c, d, acting on a complex number z, which is in the upper half plane, is going to be given by az plus b over cz plus d. And it's not really particularly hard to show that Actually, we can say a little bit more that PSL2R acts on the upper half plane, so a fortiori, PSL2Z does as well. It's not too hard to show. You can show that it preserves a real line, et cetera, et cetera, et cetera. Now, an aside that I'd like to point out is this action has always seemed a little bit mysterious to me until I realized that what this really is this is actually just the action of SL2C acting on C2, and then when you sort of projectivize that action, this is exactly what you get. So this whole thing seemed mysterious to me until I thought of it in that context, but for our purposes, we have this action here. Okay, now let gamma be some subgroup of PSL2Z. Now, when I say some subgroup, there's actually usually some restrictions we're going to impose on this. For our purposes, this doesn't really matter what those restrictions are. We want it to be a finite index subgroup. Actually, that's important. And we actually want it to be a congruent subgroup, which means that it actually has a subgroup that's of a particularly nice form, but that's not hugely relevant here. So just some subgroup that's at the very least finite index. Now, here's our definition. We say that a function f from the upper half plane to the complex numbers is a modular form of weight k if, well, it satisfies two properties. F of az plus b over cz plus d, so obviously we're using that action that I just wrote down there, is going to be equal to cz plus d to the k f of z. So it obviously satisfies some transformation law with respect to the action of PSL or gamma. So for all a, b, c, d in gamma, sorry, I should say something. We say that a function f from the upper half plane to C is a modular form of weight k for the group gamma. Obviously, the group gamma should come into this somehow. And then the other condition that we care about is what they say, that we want the function to be holomorphic at infinity. And I won't exactly say what that is just yet. I'll say what it is in a little bit later, because it's a lot easier once we talk about the Fourier expansion of this. But so these two conditions basically say that if a function satisfies these, then it is a modular form. Now, why do we have this definition? What does this actually mean? I mean, it's certainly nice. It's an automorphic function of some kind. It has some nice behavior in terms of some group. But what does this actually tell us? Well, it turns out that so this is really just saying that this is actually going to be a section of a line bundle. And I'm going to put a little star next to line bundle, since what I'm actually saying is not really correct, but in a suitable orbifold interpretation, what I'm saying is correct. It's a section of some line bundle star over the upper half plane modulo the group gamma. And the way we see this is we look at the projection of C mod H. Well, we have this natural projection map here, and what we do is we act by gamma on both of those things, where the action of gamma on C is given by multiplication by Cz plus d to the k. So we actually get some sort of orbifold line bundle over here, and all we're saying is a modular form is actually just a section of that bundle. So this sort of gives a nice geometric interpretation of what modular forms actually are. Okay. Pardon? Sorry, say that again?
Two means that I found that I can go forward.
Yes, that's correct, yeah. I mean, there's a number of different ways you can think of it, and that is, it does extend to infinity, so it extends to a compactification of that. What it's going to actually be in terms of our view is that when we write the Fourier expansion, that we don't end up with any 1 over q terms. Okay, so now this is a wonderful definition. It's all very beautiful, blah, 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 blah. Of course, you can define all sorts of great functions. If you don't have any examples, what are you doing? So let's make sure that there are, in fact, modular forms, because otherwise we may as well stop this talk right now. So it turns out, yes, there are modular forms. And the most famous of them, and actually I think basically the modular forms that started this whole thing, are the Eisenstein series. As well, G sub 2k, and it's important we actually pick these to be even. You can actually show that for PSL2Z, for the full modular group, that there are no odd weight modular forms. This is not particularly hard, and I'll probably leave that as an exercise for the afternoon. So these ones are even weight, and this is given by, so the sum over, oh, I guess it should be a function of x in the upper half plane. All pairs mn which are not 0 of 1 over mx plus n to the 2k. Now, I should actually make one specification here. For k greater than 1, this is modular. You can certainly define this for k is equal to 1, but it turns out that for k equal to 1, that we get an Eisenstein series, just not a modular form. Now, why is this modular? Well, it's actually not too hard to see. So why is this a modular form? Well, it's worth noting that we can simplify our lives a lot easier. We don't actually really need to check for every single element in whatever congruent subgroup we're talking about. We actually really only need to check for the generators. Yeah, it's worth noting these are modular for gamma is equal to PSL2. Most of the time throughout the rest of this talk, every time I say modular, I'm really actually going to mean PSL2Z. It's the Eisenstein series only care about PSL2Z, so while you can have a richer theory by talking about other subgroups gamma, we don't need to worry about them for this purpose. So why is this modular? Well, we only need to check for generators. And it turns out that for this group here, we actually have two really nice generators. We can have generators x maps to x plus 1, which of course this is the matrix 1, 1, 0, 1. We also have x maps to minus 1 over x, which is the matrix 0, 1, minus 1, 0. So these two matrices are all we actually really need to check things for. And this one here, if you just look up there, this one's actually pretty obvious. If we shift x by 1, then since m and n are integers, that actually, is fine. This one here is a little bit trickier. But it does turn out that this actually does behave reasonably well. But while it does behave reasonably well, we actually can see right off the bat why there might be problems with G2. So G2k of minus 1 over x is going to be equal to, well, the sum over all those terms is written before, 1 over, then minus m over x plus n to the 2k. Right? Well, we can just now pull out a nice factor of x to the 2k, and this gives us x to the 2k, the sum 1 over m plus nx, the 2k. Now, there is a little bit of sleight of hand here, which is part of the problem. Well, the sleight of hand basically involves that we actually switched the order of summation. And if that sum is absolutely convergent, there are no problems. The problem is that with G2, the sum is not absolutely convergent, and so we actually do end up potentially with a problem, which actually is a problem. And so due to this, G2 of x is not modular. Okay. So here's our main examples of modular forms, is the Eisenstein series. They're actually pretty nice functions. They're pretty easy to write down. They're pretty explicit. And it's actually really easy to see why they're modular just by looking at this sort of transformation here. Everything for these things behaves pretty well. As we said, though, that G2 is not modular, be that as it may. Now, the thing about this is kind of our important friend right here. Well, if you look at the transformation law for modular form, this matrix here actually does nothing, if you look up there. And it turns out that means that this is invariant under this, or it's a periodic function, so it has a Fourier expansion. It's going to give it a sum of d is equal to, well, in principle, we don't really know how far down this could go. In principle, it could go down further, but the condition that it be holomorphic at infinity means it actually starts at 0. And we had a d q to the d, where q is equal to e to the 2 pi I x. So we get a nice Fourier expansion. And in general, what we care about with modular forms, and this comes back to my statement that I think of them as generating functions, is these coefficients are often pretty nice. And you can think of a modular form actually just as this formal power series, even though it actually does have some analytic properties. Okay, so yeah, so actually this is a Fourier expansion at infinity. I actually worked this out that as x goes towards infinity along the imaginary axis, q goes to 0. So this is in fact basically an expansion of our function around the point at infinity, which is why we say it's holomorphic at infinity by looking at this thing here and saying that we start at d is equal to 0. If we had any negative terms, it wouldn't be holomorphic at infinity. Okay, so that's the definition of modular forms. What properties do they have? So the next main property that's actually pretty nice for these things is that if you take the collection of all modular forms together, they're kind of nice. Now again, we should fix a group gamma. We note this as m star of gamma is going to be given by the direct sum from k in the natural numbers of mk of gamma, where these are the weight k modular forms. This thing here, well, it's not too hard to show that you can multiply modular forms together and you get modular forms still. That transformation law that I've just erased is pretty easy to see that they multiply together well, and they actually multiply in such a way so as to respect the grading that we get on here. This is a finite dimensional, or finitely generated, finitely generated C algebra. Now, the nice thing about this is that we can often then say a lot about our modular forms just by looking at a finite number of coefficients. If we know what the generators of our algebra of modular forms happen to be, then just checking a couple coefficients lets us determine exactly what something is in that basis. You can also sometimes even check whether something is not modular by showing that you can't write it as a finite linear combination of your generators, and you only have to check finitely many terms. So this is a nice property. Now, in particular, for PSL2Z, we can write down these generators explicitly. This is simply going to be isomorphic to C of G4 and G6. These generate the entire thing. Now, one thing about this that I should actually note is when I write G4 and G6, I'm writing these things up here. It is worth noting there are a lot of different normalization conventions that we use for modular forms, and they're going to come up in the next 35 minutes. That there's, I think, 3 main ones that people like to use. This is kind of the natural just definition of G2K, although I think sometimes you put a 1/2 in front of it. There's a bunch of other ones. These have lots of pi's in their coefficient, so we sometimes like to get rid of those, but we'll sort of see how that comes out in a moment. And then note that G2 is not here, but it's something pretty nice. Now, there's a couple nice corollaries of this. And so we haven't actually seen what the Fourier expansions of these things are, but they have pretty nice Fourier expansions. And this ends up being sort of convenient for us. Since G4 squared is going to be, well, it's proportional to G8, right? If we think G8 is a modular form, it's going to be, the next thing over here. G4 squared is a modular form of weight 8. G8 is a modular form of weight 8, so they have to be proportional to each other if this is the entire algebra of them. We also have G4, G6 is proportional to G10. And by the time we get to the weight 12 modular forms, it's a little bit messier. But the point is, these relations here already can tell you a lot about the Fourier coefficients of these functions when you work out what these are. So that's already pretty nice. Yeah, well, and you get that these are dimension 1 by just looking at what this algebra is. If you work out that this algebra here, well, in weight 4 we have exactly one thing. In weight 6 we have exactly one thing. In weight 8, well, the only thing in here that's of weight 8 is G4 squared. And G8 also is of weight 8, therefore these are proportional to each other. And similar with weight 10. But in weight 12, however, you have already G4 cubed and G6 squared. These are actually not proportional to each other. So we start actually getting more messy things in higher weights, but in low weights we can say some nice things. Okay. Now, speaking of weight 12, something actually interesting happens for the first time in weight 12. So there's a certain, if we note that if we look at these things here, they all are holomorphic at infinity, but they all have non-zero constant terms. In weight 12, we have the first time where that's not true. Cusp form is a form which vanishes at infinity. So in particular, we can write it as, if we write its Fourier expansion, f of q, it's going to be equal to q times g of q, where this is some holomorphic. So these are a particular class of forms. The first one we actually see that is a cusp form is at weight 12. And if you play around with it a little bit, you can find some multiple of g4 cubed plus some multiple of g6 squared that actually gives you a cusp form. And in particular, we can actually even write down what that cusp form is. Let delta of q, so I'm going to write it in terms of its Fourier expansion because that is actually the most reasonable thing to do. It's q times the product, k is equal to 1 to infinity, of 1 minus q to the k to the power 24. So now it's worth noting that if you're familiar with the eta function, this is eta of q to the power 24. I mean, if you're familiar with the eta function, you actually probably already know what modular forms are, so this is probably not the most relevant part of the talk. But if you are familiar with it and didn't know what happens to be a modular form of weight 1/2, then this is true. But anyway, so this function here is a cusp form of weight 12. And it turns out that under appropriate normalizations that it is, in fact, that, some multiple of g4 cubed plus some multiple of g6 squared is, in fact, this thing here. And again, you can work these out. Normalization conditions make this a little bit better, actually. If we normalize g4, g6, so as to have constant term 1, well, then we can actually see right off the bat that we write these as E4 and E6. So as I said, there are a number of different normalization conventions, and G4 and G6 happen to be the way that we wrote them down originally. But if we normalize them so they have constant term 1, we write them as E4 and E6 respectively. And just so we're clear, let's write this out as E4 is equal to 1 plus 240, the sum b is equal to 1 to infinity of akq, or adq to the d, and E6 is equal to 1 minus 504, sum d is equal to 1 to infinity of bdq to the d. And I will leave those ADs and QDs for you guys to figure out later in terms of what they actually are. They're very nice in terms of sums of divisors. And it's a good exercise, build character once in your life to actually compute them. Then it's pretty easy to see that E4 cubed minus E6 squared is equal to delta. And it's simply, oh wait, no, that's not right at all. I think it's over 1728. Well, because that gets rid of the constant term, so it's a cusp form, and then if you work out what those things have to be, that's what it is. Anyways. Okay. Yeah. Okay. So here's some examples of modular forms. They're very nice things. Again, I really do think of them as generating functions because they actually do, oddly enough, seem to show up a lot. Now, the question is, of course, where do these show up? If I'm claiming that these show up in enumerative settings, I should probably show where they do. So these are supposed to show up in some setting where we're counting something. Where do they show up? Well, the first place that they show up, and this is actually kind of one of the more obvious places when you sort of work out the details, but the first place that they show up with a little star next to that as well is in the following problem. Let n sub d denote the number of degree d covers of an elliptic curve by another elliptic curve. So, for example, the number of degree 1 covers of an elliptic curve by an elliptic curve, there's one of those. But, you know, you can ask furthermore, like, how many covers do we have of a given degree? And then it turns out that then n sub d is equal to sigma 1 of d, which is just the sum k divides d of k, so it's the sum of divisors function. And well, we can actually do a little bit better with that. Sum of divisors. Yeah, because we're summing over all divisors of d, and we're summing the divisor itself. So, again, this is something that is not too terribly hard to show, and I'm leaving it as an exercise to the viewer later. But where does this show up in terms of modular forms? Well, the answer is it doesn't exactly. If we write this as a generating function, the sum from d is equal to 1 to infinity of n sub d q to the d. So here's our generating function here, which is, of course, let's just rewrite that as sum d is equal to 1 to infinity of sigma 1 of d q to the d. Well, what is this? It turns out that this is, well, almost proportional to E2 of Q. Almost. Up to a constant term. So it's worth noting that what I've written down does not, in fact, have the constant term. That's why it's, maybe I should put that in quotes. It's not actually proportional to it because it has no constant term. Though it is worth noting, and this is something that I admittedly don't understand as well as I would like to, there is an interpretation of the constant term in this in terms of something that looks sort of like counting covers, which I've still never really completely understood. It has to do with the Euler characteristic of M11 bar, but be that as it may. Now, of course, I've just spent the last half hour lying to you guys in that I've been claiming that modular forms have enumerative significance, and I've said this is not modular. So how do I actually reconcile this? Well, the thing is that modular forms themselves do have enumerative significance, but only in a slightly broader setting. And that broader setting is if we actually allow that thing into the club. So although that being said, I maybe should at least outline exactly how this proof works. So the proof sketch, well, we're counting degree d covers of an elliptic curve. of some elliptic curve E1, which of course an elliptic curve is always given by the complex numbers modulo some lattice, is given by an index D sublattice of lambda 1. Say lambda 2 contained in lambda 1. So certainly if you have an index D, oh, I didn't write the D, I said it out loud. Index D sublattice of lambda 1. So certainly it's clear that if you have such a sublattice, and then you take C mod the one lattice, and you get a map to C mod the other lattice, that does give you a degree D cover. But it's actually not too hard to show that, in fact, the converse is true as well. But so a degree D cover of an elliptic curve is really just given by an index D sublattice here. And then, i.e., a matrix A, B, C, D with A, B, C, D are integers, and of course AD minus BC is equal. Yeah, I shouldn't really use the same D there. ABC delta. I really should not have used the same letter there. So A delta minus BC is equal to D. Now, it turns out that by an appropriate change of basis, that this is really just written by, well, A, B, 0, and delta, with A delta with A delta is equal to D, obviously that gives you the same determinant, and 0 is less than or equal to B is less than A. And so with these two conditions here, you can kind of see that that gives us exactly the sum of divisors. In that for every divisor of D, we can choose, you know, a divisor here and D less than that divisor. And what we're doing is we have, well, each possible choice of B here gives us a different elliptic curve. So that gives us exactly what we're looking for. Modulo a couple assertions in that proof that I am not actually proving, but give or take, that's the proof. Okay. Anyways, but back to the original problem, is that I'm claiming that modular forms have enumerative significance, but here I'm suddenly saying this thing that is not a modular form is actually what we're interested in. And so we just need to, it turns out, expand what we care about. And this is where quasi-modular forms come in. So, first of all, I should say that there are a lot of different ways of defining quasi-modular forms. There's the way you could define them that makes them really easy to identify, or there's the way that actually sort of makes sense and is sort of a little more motivated. And I'm going to go with the more motivated one. So, so we need to expand. We need to expand our notion of modularity. We want to include this G2 or E2. Or E2, depending on your choice of normalizations. And let's just write down what E2 is. Well, E2 is going to be 1 minus 24, the sum from D is equal to 1 to infinity, sigma 1 of D q to the D. So you can see that's, of course, what we wrote over there, at least up to a constant of proportionality, minus 24. So we want to include this into the party, and how do we actually justify that? Well, we get the following. So this is not a modular form. I can't stress that enough. However, if we look at some related function, e2 tilde, which is given by e2 minus 6i over imaginary part of x. So of course, this is not holomorphic. This thing here is actually modular. It's not holomorphic, but it is modular. So this thing here, which is really, we haven't added that much. We've got a constant divided by the imaginary part of x. It's really not the most egregious anholomorphicity that you can add into something. But when we just add that little bit of a tweak, we actually get something that is modular if it's no longer holomorphic. And so using that as a motivation, so with this motivation, we define definition. An almost holomorphic modular form is a function f of x, which is going to be equal to the sum from, say, k is equal to 0 to r. I should actually say actually d is equal to 0 to r, of weight d, depth at most r, so this is, of course, that r that we're talking about. So we want to write this as a sum f sub d of x times the imaginary part of x to the minus d. Oh, yeah, sorry. This should, I wanted that to be weight k. Sorry, thank you. So of weight k, depth at most r is going to be some function of this form, which transforms like a modular form of weight k. So if you look at this thing here, of course, this E2 tilde is in fact an almost holomorphic modular form of weight 2 for the exact reasons that this thing here, well, this thing transforms like a modular form of weight 2, and it's exactly of that form there. Now, given such a definition, which E2 tilde is, how do we get to quasi-modular forms? Well, quasi-modular forms is pretty easy at this point. Then a quasi-modular form of weight k is simply the constant term. Constant term with respect to imaginary part of x to the minus 1. So an almost holomorphic modular form is something that transforms like a modular form, but it's got these sort of anholomorphic terms that are polynomial in imaginary part of x inverse. And the quasi-modular form is in the constant term. Now, there's another way of thinking about this, or it is the limit as x bar goes to infinity of f of x, where f of x, I guess I should really be specific, and f of x, x bar, is an almost holomorphic. Now, the reason I write this slightly alternate form is that when it comes down to talking about things in enumerative geometry, when it comes down to mere symmetry, we are often interested in the large complex structure limit, and that's exactly what this is supposed to represent. Okay, so the one thing this definition does right off the bat here is it makes it absolutely clear why E2 is this new thing called a quasi-modular form. But one thing you always have to make sure that you're not doing is if we introduce this new definition, I mean, how much is this expanding what we have here? Is this turning something into this horrible, horrible mess? Maybe we've just expanded it so that every function is secretly quasi-modular, which would be an utter, utter disaster. And fortunately, that's just not true. In fact, this really is almost the most minor of changes that you can possibly do. So theorem, let Q mod star of gamma denote the ring of quasi-modular forms, or the algebra of quasi-modular forms. Because they certainly form an algebra. It's not too hard to see that if you multiply two of those things together, you're going to get something that's similar to that form, the constant term, et cetera, is respected, so we're fine. So we have an algebra here. And of course, mod star of gamma is going to be the ring of modular, or the algebra of modular forms. So we want to know what's the relation here. And the relation is very, very simply Q mod star gamma is isomorphic to mod star gamma with one small addition that we add in that polynomial ring on one generator. That's it. So it's kind of amazing that adding this sort of, I mean, maybe that's not that amazing in that it isn't really, it's obviously not the case we're allowing every function in here, but realistically, this definition is almost tailored towards really just allowing G2 or E2, depending on your normalization, into the club. And it does that perfectly. Now, why is this true? This is true for any group, actually. So yeah, sorry, I should have been clear. This is actually true for any group gamma. It's also in particular true for PSL2Z, but it's also true for your favorite congruent subgroup as well. And that's actually something that's less obvious, but the proof of the theorem actually goes through identically. So essentially what we do is we take a function like that, given f in Q mod star of gamma, what we do is we just induct on the depth. And it turns out that, i.e., if f is the constant term, I should say f naught. So we have f is equal to the sum d is equal to 0 to r of f d imaginary part of x to the minus d. So we have some expansion here, and of course the constant term is a quasi-modular form. Then, well, f minus fr times 1 over 6i times g2 to the r. Actually, it is worth noting that I have something funny. Then I've got something a bit off about my normalization here. So I think if I've written this is not technically correct. There's a constant off about that normalization. But the point is that, give or take that, this thing here is, well, it certainly fits. We're all just playing with adding copies of G2. And you can show that these themselves actually satisfy the right transformation law. And this thing here ends up being, actually I really should do that, is a almost holomorphic it's an almost holomorphic modular form, but now it's of smaller depth. And so just by inducting on the depth of our almost holomorphic modular form, we actually are able to just take away copies of G2 until all of that goes away. And so that gives us what we're looking for. So again, amazingly enough, that really, no matter what congruent subgroup we're talking about, we're really just talking about adding copies of G2 into the club, so to speak. Okay. So these are quasi-modular forms. As I said, they're basically tailor-made so that we can include G2 into the party. Now, just one quick crawler, I guess I should say. Q mod star of PSL2Z. This is isomorphic to C of G2, G4, G6. Now, there's also another thing that is not immediately obvious, but is not so bad just due to the fact that all we're really adding is G2. But you can also show that Q mod star of gamma is closed under differentiation. So if you tried to take the derivative of a modular form, you'd see pretty easily that it's tantalizingly close to being closed under differentiation. It's very, very nearly the case that it really gives you, take the derivative of a modular form of weight k and you get 1 of weight k plus 2. It's almost the case, but not quite. And basically that difference really just comes from, it actually lands you in the algebra of quasi-modular forms. So that's actually a nice property that this has here. Okay. Now, what we would like to do is we'd like to sort of now take all of this. This is, just algebraic constructions we're talking about at this point, with the exception of a brief moment where I did talk about some enumerative interpretation, at least for counting elliptic curves. So where else does this actually show up? Where do we actually get these to show up naturally in the enumerative world? Well, obviously, aside from the one example that I've already stated. And it turns out that they actually show up in a lot of places. So the first place that I'm going to point out that they show up is, well, I mean, a lot of these, okay, not a lot. Some of these come from mirror symmetry. And in fact, the first case I'm going to show up really comes directly from mirror symmetry. Mirror symmetry for the elliptic curve. Actually, a little more than that, higher genus mirror symmetry for the elliptic curve. So without going into too much detail about that is, mirror symmetry, of course, as everyone hopefully has at least heard, some words about, is saying that, you should have these pairs of manifolds where the complex moduli space of one manifold is sort of matched up with the Kähler moduli space of another one, but only if we're talking about these large complex structure limits, which of course, that sort of stuff here is sort of tailored towards. But that's not really necessarily the focus of this. I mean, it's a nice thing, and that'll come up, I think, in a lot of other places. But this is something that does come out of that, actually. For the elliptic curve, mirror symmetry actually gives us something really nice. So let n, d, g, and let's be specific for E, denote the number of degree D genus G covers of E for g greater than 1. So it's worth noting that we already did see the case g is equal to 1. And now we'll talk about, well, we could have higher genus covers. You can talk about genus 2 covers of an elliptic curve. You can talk about genus 87 covers of an elliptic curve. That's perfectly fine. We can ask, well, how many of them are there? And then we get that then, if we let fg be given by the sum d is equal to 1 to infinity of n dg q to the d. So again, we basically build a generating function. Oh yeah, thank you. So we build a generating function of these numbers here. And as I said, I really do think of these very often purely in terms of formal power series, but there is secretly an e to the 2 pi I x sitting here. Then this function here is a quasi-modular form of weight 6g minus 6. So the original proof of this is, well, the original relatively coherent proof of this is due to Dietgraf, but that's not really a proof. It's more of a physicsy proof. I think the current full proof of this, I think the only place it's really shown up, because you and Mike Roth have sort of partial things, but not completely, and I think the only thing is Seeley's thesis, I think, is the first place that a full proof of this actually shows up. Computational proofs can be shown for low genus, but it's, I think Seeley's is the first that actually properly proves this. But it's a very beautiful statement. Oh, sorry, there's some normal, I'll just put a proportional there. So we had a quasi-modular form showing up of weight 6g minus 6. So this is a case where a relatively easy to describe enumerative problem, counting covers of an elliptic curve, gives us quasi-modular forms. And then a couple quick ones, because I'm running out of time. So, case 2. So we can now talk about K3 surfaces. A polarized K3. And let, similarly, n dg K3 be the number of d-nodal genus G curves in X. So we have a polarized K3 surface, and you can talk about curves on that K3 surface, and they have a genus, they might have some number of nodes. Then what we find is that the generating function for these things, some d is equal to 1 to infinity of, I could probably say d is equal to 0 to infinity, n dg K3 q to the d plus g minus 1. So we build a generating function, which has got a little bit of a funny shift in there, is actually equal to d g2 to the power g over that discriminant modular form. And it is worth noting that this is, I'll put a bar here because that's not the normal normalization. Unfortunately, the reason that I'm getting my normalizations messed up here a little bit is that there are usually 3 different normalizations one uses and 2 letters that people use to denote them, which is sort of frustrating a little bit because G and E are the letters you always use, but there's 3 normalizations. Which do you pick? Anyways, so, but the point is that we are counting curves in a K3 surface, and it turns out, once again, we get quasi-modular forms. I mean, this is obviously a modular form, but this is G2, which is quasi-modular, and it's the derivative of that. I guess I should specify, where D is equal to Q d by dq, which is this so-called logarithmic differentiation. And then finally, something relatively near and dear to my heart. Oh yeah, sorry, this is originally conjectured by Yao and Zaslow, and then it sort of fits into a grand scheme of counting curves and surfaces by Gutsche. But the first proof of this, at least for primitive classes, was by Brian and Conan Liang in 1999 or something like that. It's a beautiful paper. It's very easy to, well, relatively easy to understand, which is kind of nice. It's just straight up combinatorics for some parts of it. And then case 3, as I said, near and dear to my heart. Let n abelian g denote the number of hyperelliptic curves in an abelian surface A up to translation. Now, of course, you have to verify that these are actually well-defined enumerative things, and strictly speaking, actually, that should pass through some points. But number of hyperelliptic curves in an abelian surface up to translation, then the sum from d is equal to 1 to infinity of n abelian g d q to the d. And I'm just going to say this is also a quasi-modular form, and I'm not going to specify specifically how it is written, because there's a couple other details that go into actually making this well-defined. It's a pretty nice formula, but it's a little bit more complicated than the ones I've written above. So I'm just going to say that it is a quasi-modular form, and you can actually write it down explicitly, and it's very nice. Anyway, so these are just a couple examples where these things actually naturally show up. Case 2 is actually maybe a little more representative of surfaces in general. It turns out there's a really beautiful theory of counting curves on surfaces, and this is just a specific instance of that. Hyperelliptic, well, that's kind of adding a new thing, but the point is that a lot of enumerative problems really come down to producing generating functions that happen to be quasi-modular forms, and that's a very nice thing.
So the case 1 is more quasi-modular for PSL.
Yeah. Yeah, it's worth, okay, that's a fair point. Sorry, case 1 and case 2 are for PSL2Z. This is actually for a congruent subgroup, and this is the first time out of the stuff I've been talking about where we actually need to step down to a proper subgroup of PSL2Z. But it's not a particularly crazy subgroup, so. Anyways, and that is my introduction to quasi-modular forms in an hour.
Any questions? Comment?
So can you write a description of that class series as something like
So I can, as I said, that there's actually a couple finicky details, because when you have hyperelliptic curves in an abelian surface, you have to care about where the Weierstrass points end up. So because of that, I was choosing not to, but give or take, that it ends up being equal to some function which isn't not the same e at all that I've used before, e of q, times some function where we're taking a product over a certain set of two torsion points of some functions a k of v q times the rest of the points v naught in p of some other collection of functions c k of v of q. And so, oh, well, this is q to the 4 and q squared. And so you get some function, like, these are explicitly describable things, and you have to be a little bit careful what this subset of two torsion points is and what these functions are. There's some finicky details just to state it properly, but the point is you can actually describe it explicitly. And those functions themselves are actually pretty nice. It's just, it's a little bit messier, and we would need like another 5 or 10 minutes to properly write that down.
The weight.
The weight of, actually, that's kind of a funny thing, because we're having 1 over delta of q.
Well,
Yeah, so it's the weight of that is going to be, I guess it would be, yeah, so that's weight 4g minus 12. Yeah, and I mean, it's worth noting that this, it's kind of a funny thing that we have this weird weight there, the fact that the weight is going to be negative. It just is. I mean, there's nothing wrong with having negative weight modular forms. I mean, think of them as sections of line bundles. It's sections of the inverse bundle. That just happens to be what shows up. So, and the integer coefficients, which is of course important.
Maybe somebody is talking in the workshop about the BPS counting.
Yeah, actually, that's a fair point. So it's worth noting that BPS counting is not something I completely understand, but my knowledge. So the way that that actually is proved, again, it is a really beautiful paper, is that's proved by talking about the Gromov-Witten invariance in a certain sense of a K3 surface, and then you relate the Gromov-Witten invariance to these so-called BPS states, which actually in that case I think are the same thing because it's primitive classes. But for non-primitive classes, you have to start paying attention to your BPS states versus Gromov-Witten invariance, and there's all this whole Gopakuma-Vafa stuff coming into it, and that's just a mess.
Questions? Okay, so we'll meet at, well, maybe we can take 10 minutes break. Yeah.
I guess you never saw my talk, that's what you were asking that question.
Yeah.
In my talk, I essentially gave a
Yeah.
how many this would be better to really know how much modular forms people know, and I have no idea.
More or less